Welcome to the first of the many video lectures that I plan to do this semester. So basically these video lectures will be some topics which are already taught in the lectures in the class, but which I feel needs more explanation for your better understanding. So we will start with the digital communication concepts of discrete memoryless channels. So first I will go through the concepts of the Arg Max function that you came across in your discrete memoryless channel analysis, and then I will go into the actual discrete memoryless channel analysis once more, and I will solve an example to explain the concepts a little better than that was taught in the class. Okay, so let's start. So what is Arg Max? So Arg Max, basically, as you saw in the class, it gave you those values of x that maximizes the value of the function fx. So fx is a function of x, and over the domain of that function, which means the all possible values that the function can take, you will have a certain maximum, or you can have multiple maximums, and arg max x will give the values of x at which your function is maximum. Okay, so for example, in this diagram, as you can see, you have this function fx which is plotted, and it has in this case only one global maxima, and that is given by max of fx, and the maximum value is 0.8, and the value of x that gives this maximum value, which is 0.8, is 0.4, and that actually is your arg max of fx. So arg max again gives you those values of x at which the value of fx is maximum. So note that if a function does not have a maxima at all in a given range of values of x, then argmax will be an empty set. So there might be a situation when the function doesn't have a maximum at all. Okay, so in that case argmax will be an empty set, and like argmax, max may be also an empty set, by the way, or a singleton. So singleton means a set with only one value. Okay, so argmax and max can be empty set or a singleton, but unlike the argmax, max may not contain multiple elements. Okay, so what does that mean? So if you look into the function here in this diagram again, you can see that it gives two maximum. Okay, and the value of that maxima is same, and that is equal to 4. So if you take the maximum of that function, which is defined as 4 of x square minus x to the power 4, if you take the maximum of that function over all values of x, then it gives you 4, even though there are two maximum values, two peaks you can see from the diagram, but those two peaks have the same value, 4. So maximum of x returns you a singleton, or a set with a single element, but arg max of x, that is those value of x that gives the maximum, it will return two values, because in this case you can see that at minus of square root 2 and plus square root 2, your function 4 of x square minus x to the power 4 is maximized, even though the value of the maximum, two maximum values are the same, which is 4. So these are very subtle differences between argmax and max, but the idea is that your max function gives you the actual maximum of the function, and your argmax gives you that value of x for which the function fx is maximum. So argmax can operate both for continuous functions and discrete functions. So here you can see we have, let's say, a continuous function at the top, and at the bottom I have the same function which is the sampled version of the first function. So you have discrete values in the bottom function for different time values, and the top function is continuous in time. But for both the functions you can define argmax, and in this case for both the functions your argmax over all values of x is basically 21, because 21 is that value for which these two functions give the maximum value. So here your x-axis is time axis, so the values of x is basically the values of time, and your fx is basically the amplitude in this example. So we can have argmax for both continuous functions and discrete functions. Whichever value gives the maximum of the function, your argmax operator returns that value, or it can also return many values, as you saw in the previous case here. So here it returns two values for the argmax operator. So let's see another example. So let's say we have a function fx which is defined as 3 of x square minus x cube minus x to the power 4, and this function is plotted here in this diagram. So your x-axis gives the values of x, and your y-axis is the values of fx, and you have this function. So you can see this function has two local maxima, okay, but one global maxima. What does that mean? You can see that there are two peaks of this function, but one peak is greater than the other peak. So if you speak globally, this function has one maxima, but if you only focus, let's say, at the positive values of x, the values of x greater than 0, then you can see from the diagram, for those values of x, the maximum is the one on the right of your x-axis, and that value is less, by the way, compared to the other maxima that you have on the left of the x-axis. So the other maxima which is on the left of the x-axis is higher than the maxima on the right of the x-axis, so therefore that maxima is the global maxima. So now if we want to find, let's say, the argmax, or the argument of the maximum of fx for the range of values of x between minus 2.5 and 2.5, then how do we approach? Okay, so let's say we take some values of x and some values of fx corresponding to that values of x, and see where our maximum of fx occurs, and that value of x for which the maximum of fx occurs will be the argmax of fx. Okay, so let's say at minus 2.5, we have to start from minus 2.5 because we are interested in this particular range between minus 2.5 and plus 2.5. So at minus 2.5 I can see that the value of fx is minus 4.6875. This can be easily found if you plug in the value of x to be minus 2.5 in that expression 3x square minus x cube minus x to the power 4, you will get minus 4.6875. Moving on, similarly at minus 2 you have fx as 4, At x equal to minus 1.9, you have fx as 4.6569. At x equal to minus 1.8, you have 5.0544. So it's still increasing. Okay. At minus 1.7, it's 5.2309. At minus 1.65, it's 5.2476. Then if we have minus 1.6, it's 5.2224. So notice the value now decreases. Let's check few other values. Minus 1.5, you have 5.0625. So the value again decreases. Let's be a little more sure. Let's check with x equal to 0. We have then fx equal to 0, and then for x equal to 1, we have fx equal to 1. For x equal to 1.5, we have fx equal to minus 1.6875. So doing this exercise, we can see very clearly that at minus 1.65, your fx is maximum, which is 5.2476. So therefore, the arg max of fx, which is that value of x that maximizes fx, is actually minus 1.65. So this is the value that maximizes fx over all the values of x that is between minus 2.5 and 2.5. So that's the entire concept of arg max. So similarly, you can also have arg min, which means that value of x that minimizes the function fx. So we can find out arg min. Similarly, we found out arg max. Okay, given a function, we can do that. So arg max and arg min are two operators that actually finds out the values of x for which a function of x fx is either maximized or minimized. Okay. So now let's move back to the discrete memoryless channel that we covered in the lecture. So we have the a priori probabilities of the discrete memoryless channel, which are denoted by p of xj's. So this j can take any value from 1, 2, 3, 4, any values depending on how many inputs we have for the channel. And the transition probabilities are also given. So these transition probabilities actually define your channel. So they are given by the conditional probability that you observe yk at the output given xj was transmitted. So given these two sets of probabilities, probability of xj's and probability of yk given xj was transmitted, we can calculate the joint probabilities, probability xj comma yk, and they are given by the definition of conditional probabilities. So that is equal to probability of xj times probability of yk given xj. So you know probability of xj and you know the probability of yk given xj's because those are the transition probabilities. So you can easily calculate the joint probabilities. Now once you calculate the joint probabilities, you can calculate the probability of yk's by summing the joint probabilities over all values of x. So whatever be the value of j, you can sum over all those values, j equal to 1 to m, and you get probability of yk. So if you sum the joint probabilities, you get the conditional probabilities, marginal probabilities of yk, and that is given by that expression, probability of yk equal to sum over all j's probability of xj comma yk. And then you can write probability of xj comma yk as probability of xj times probability of yk given xj. And finally, you can calculate the a posteriori probabilities, which are defined as probability of xj given yk. So this is different from the transition probabilities. The transition probabilities are given as probability of yk given xj. So the yk comes first and xj comes next. In case of a posteriori probabilities, your xj comes first and then yk comes next. So basically this is the probability that xj was transmitted given that you observe yk at the output. And this can be easily calculated in terms of the joint probability and the probabilities of yk. So you see, you start with probability of xj, which are your a priori probabilities, and the transition probabilities, probability of yk given xj, and you can step by step calculate the joint probabilities, the probability of yks, and the a posteriori probabilities, that is probability of xj given yk. For all values of j and k, you can calculate these easily. Okay, so we will see now with this example how you can calculate all the probabilities given the input probabilities and the transition probabilities. So in this example, let's consider a discrete memoryless channel with two inputs, x1 and x2, and three outputs, y1, y2 and y3, and the two inputs are equally probable. Let's assume in this case that the two inputs are equally probable with probabilities half each. Okay, and now you have these transition probabilities. Okay, so what is the probability of receiving y1 when your x1 was transmitted? That probability is half. Next, what is the probability of receiving y2 given x1 was transmitted? That probability is 1/3. What is the probability of receiving y3 when x1 was transmitted? That probability is 1/6, and so on. So in this way you can have 6 different transition probabilities. And why 6? Because you have 2 inputs and 3 outputs. So 2 times 3 is 6. So in any discrete memoryless channel example, the total number of transition probabilities that you can have is basically the number of inputs multiplied by number of outputs. So here you have all 6 transition probabilities whose values are given, and you have the input probabilities, which in this case are the same. So now let's say if I want to calculate the joint probabilities, all the joint probabilities, probability of x1 comma y1, probability of x1 comma y2, probability of x1 comma y3, probability of x2 comma y1, probability of x2 comma y2, and probability of x2 comma y3, then we can easily calculate those from the given information that we have. So we can write that probability of x1 comma y1 is equal to probability of x1 times the probability of y1 given x1. So this step is same as the first step in this slide. So we are actually calculating the joint probabilities, probability xj comma yk, okay, from the input probabilities or a priori probabilities and the transition probabilities. So here my a priori probabilities are given, probability of x1, probability of x2, both are half, and my transition probabilities are given, all those 6 values that you can see. So I can easily calculate the joint probabilities, and I can calculate them like this. So I multiply all the associated terms and I get probability of x1 comma y1 as 1/4, probability of x1 comma y2 as 1/6, probability of x1 comma y3 as 1/12, and so on. Okay, so I have all 6 joint probabilities. Now I can calculate the probabilities of the yk. So in this case my yk runs from y1 to y3. So k is 3 in this example. We have y1, y2, y3. So these are my yks. where k equal to 1, 2 and 3. So I can calculate probability of y1 by summing the joint probabilities of x j comma y1, where j can have only two values, because in this example x takes two values, x1 and x2. So basically I sum all the joint probabilities that involves y1, and then I have x1 y1 and x2 y1. So I sum over all the values of x, keeping y1 intact. Okay, so probability of y1 is actually the sum of all the joint probabilities that includes y1 as the last variable. Okay, so probability of x1 y1 plus probability of x2 y1 in this case. If we had more inputs, all values should have been added. Let's say if we had 3 inputs, then we should add probability of x1 y1 plus probability of x2 y1 plus probability of x3 y1 to find the value of probability of y1. So this operation is again same as the second bullet point in this slide. Okay, we are calculating probability of yk for each value of k, and that is actually the sum of all the joint probabilities, keeping yk intact but summing over all values of xj. Okay, so the same thing we are doing here. We are calculating probability y1 by keeping y1 intact in the second term but summing it over all values of x. In this case x has two values, so we are adding probability of x1 y1 plus probability of x2 y1, and that gives me half. The value of probability of y1 is half. Similarly, probability of y2 I calculate as 7 over 24 and probability of y3 as 5 over 24. Now I have all the joint probabilities, I have all the output probabilities. Now let's calculate the a posteriori probabilities. So what is the probability that x1 was transmitted given that I observed y1 at the output? So that is given by probability of x1 given y1, and that can be easily calculated from the joint probability and the probability of y1. So I have in this case probability of x1 given y1 equals to half. Similarly, probability of x2 given y1 is probability of x2 comma y1 divided by probability y1, and we have again calculated these two terms previously, so we get half again. Proceeding in the similar way, we calculate all the a posteriori probabilities, probability of x1 given y2, probability of x2 given y2, and we have all these values. Okay, so now you can see that how I can calculate all the probabilities associated with the discrete memoryless channel, starting from the input probabilities and the transition probabilities. I can calculate everything. I can calculate the joint probability, I can calculate the probability of the outputs, and I can calculate the a posteriori probabilities. Now let's move on and focus on the map decision rule. So this is the maximum a posteriori probability decision rule. So in this case, as you saw in the lectures, this decision rule actually tries to estimate what was the input given you observe something at the output, and it tries to make that estimate optimum. So the optimum decision rule for map is so your x hat is basically the optimum decision, okay, of the input symbol. So given you observe yk at the output, what is the optimum decision of the input symbol x hat, and that is actually given by the arg max of the a posteriori probabilities. So if I have all the a posteriori probabilities as you can calculate from the input probabilities and the transition probabilities, then you can check with different values of xj for a given k, what value of xj gives me the highest value of probability of xj given yk. Okay, so let's calculate this for this particular example that we saw. So in this case, let's start with k equal to 1. So let's say you have observed y1 at your output, okay, and you are trying to predict what is the optimum decision, what is the best possible estimate of the input x hat. So in this case you have two inputs, x1 and x2. So whether x hat will be equal to x1 or x hat will be equal to x2. Basically x hat will be that value of x that maximizes the probability xj given yk. So in this case k equal to 1, so you have to basically calculate probability of x1 given y1 and probability of x2 given y1. So these two you have already calculated in the previous slide here. Okay, you have already calculated in the previous slide, and you can find out easily that probability of x1 given y1 is half and probability of x2 given y1 is also half. So in this case there is no winner. Okay, it's a tie. So none of these two probabilities are higher than the other, so we don't find a maximum here. So in this case you can just make a random guess and choose any one of the inputs. Okay, so you say that okay, x1 was transmitted without any choice. Okay, so now let's say for okay, so when y is observed at output, then you can see it is hard to decide what was transmitted. Now let's say for k equal to 2, which means that y2 is observed at the output. So in this case you have to find out the probability of x1 given y2 and probability of x2 given y2, and find out for which value of x, either x1 or x2, I have the maximum probability. So you can see easily that 4 by 7 is greater than 3 by 7. Okay, so probability of x1 given y2 is maximum among the two probabilities. So therefore the value of x that maximizes these two probabilities is x1. So therefore the argmax function returns me x hat equal to x1, because the value of x that maximizes the two probabilities is x1. Okay, so again if we have k equal to 3, then again we do the same procedure. So in this case probability of x1 given y3 is 2 over 5 and x2 given y3 is 3 over 5, and you can easily see that 3 over 5 is greater than 2 over 5, and therefore the argmax function will return x hat equal to x2, because for x hat equal to x2 your probabilities, your a posteriori probabilities are maximized. Okay, so this is how you approach this type of problems. Okay, so if you have again a multiple inputs, so in this case you had two inputs, if you had like 4, 5, 6 any input and then any output, the way to approach this problem is based on the input probabilities and the transition probabilities. You first calculate all possible joint probabilities, then you calculate all the output probabilities, and finally you calculate all the a posteriori probabilities as I have shown for this example. And then once you calculate all the a posteriori probabilities, you try to find out that if you observe a particular output yk, k can be 1, 2, 3, 4, anything depending on the actual number of outputs, you fix k and then see for that particular fixed value of k what value of x maximizes all these a posteriori probabilities. Okay, and that value of x is your optimum decision or optimum estimate of x. Okay, so basically why we are trying to find out the optimum decision rule, because if we find that, then if I know that what is the best possible input for a given observed output, then we can minimize the probability of error. Okay, so we'll see that later. First let me go to the ML decision rule. So in case of ML decision rule, you have so in case of ML decision rule, you have x hat equals to arg max of probability yk given xj. So this is basically the arg max of all the transition probabilities. Unlike the map decision rule, where we were trying to find out the arg max over all the a posteriori probabilities, in this case we are finding the arg max over all the transition probabilities. So in this case we have this expression. So this means so let's do the same exercise again. So in this case, let's say for k equal to 1, what is your probability of y1 given x1? And that is half. And what is the probability of y1 given x2? That is also half. So again, you cannot decide anything. So this case is same as the first case of map decision rule. Okay, again if you see for k equal to 2, probability of y2 given x1 is 1/3 and probability of y2 given x2 is 1/4, and 1/3 is greater than 1/4. So in this case, among these two probabilities, 1/3 is maximum. So probability of y2 given x1 is maximum, and the value of x that maximizes the two probabilities is x1. So therefore your optimum decision is x hat equal to x1. And then for k equal to 3, if you do the same thing, then you get the two probabilities as 1/6 and 1/4, and 1/4 is greater than 1/6. So in this case, the maximum value of the probability is returned for x equal to x2, and therefore that is the optimum decision, x hat equal to x2. Now let's calculate the probability of error. So as was shown in the actual lecture, we would calculate probability of error by first calculating the probability of correct, and this expression was shown in the class note. So this is your probability of correct. So basically if you have, in this particular example where you have 2 inputs and 3 outputs, from the above general expression we can write for this particular example probability of correct equal to probability of x hat equal to x1 given y1 multiplied by probability of y1. So when y1 is observed at the output, the optimum decision was hard to make, so we actually chose x1 in this case, but you can choose x1 or x2 because it was hard to choose, as you saw in the previous two cases, both for ML and map. Then for y equal to y2, you have the optimum decision x hat equal to x1. So I will calculate probability of x hat equal to x1 given y2 times probability of y2. That's the second term of your probability of correct expression, and then the final term is probability of x hat equal to x2 given y3 multiplied by probability of y3. So in this case, when y3 was observed at the output, the optimum decision was x hat equal to x2. So I am taking that value here. I'm not interested in other conditional probabilities. So this is something to take note of. When I'm calculating the probability of correct, I'm only taking those values of x in the conditional probability which gave me the optimum decision, okay, for the given value of y. So when I'm writing probability of y1, I will write probability of x1 given y1. When I'm writing probability of y2, I will write probability of x1 given y2. So these are the corresponding optimum values that I'm taking. I'm not taking the other values. And here the summation runs for all values of k. So here in our example, k is 3 because we have 3 outputs. So if we sum over the 3 values of k, we have the expression that's given below. Okay, so now if we calculate this expression with all the values that we have calculated previously, we will find that the probability of correct is equal to 13 over 24, and therefore the probability of error is 1 minus probability of correct, and that equals to 1 minus 13 over 24, which is equal to 11 over 24. So this probability of error is the minimum probability of error that we can have, okay, because we have calculated this probability of error using the optimum decision rule. Okay, so we have taken only those value of x in the conditional probability expressions above which gives me the optimum decision. Okay, so if I calculate the probability of error in this way, I would get the minimum probability of error. Okay, so that's the whole idea about the optimum decision rule. And that's why we are interested in optimum decision rule, because the ultimate goal of any communication system is to reduce the probability of error. Okay, so that's it. We stop this video tutorial here. I hope you can understand the concepts well after watching this video. Thank you.